as we try to find a derivative rule for every situation, we shouldn't forget about the inverse trig functions. Right? Trig functions turn angles into ratios of sides. So if we treat the angle as the independent variable, we can find the rate of change of the sides in a unit circle or right triangle kind of situation. But what if the side is the independent variable and we want to find the rate of change of the angle? That's this kind of situation. So suppose we have an object moving counterclockwise, I guess it should be clockwise, around a part of a unit circle, so that after t seconds its x coordinate is t, so this point is moving this way. So the x coordinate of the point right here is increasing. You can see an increase in this x value, which in this case is just t, causes a change in this angle over here. So how fast is this angle changing as a function of t? Well, to figure that out, we first need to describe this situation geometrically, or find a relationship between theta and t. So we're in a unit circle, so this hypotenuse is 1, we have this right triangle, and so in this situation, the x coordinate of the point is cosine of the angle, right? Really, it's the x coordinate of the point divided by the radius of the circle, but that's 1 in this case. So x is cosine of theta, but if we want to treat, and x is t, right? So if we want to treat t like the independent variable and theta like the dependent variable, or the function, then we actually need to solve this equation for theta. I'm sorry, solve it for theta. So take inverse cosine on both sides, and you get theta is inverse cosine of t. So the rate of change of theta as a function of time, that would be d theta dt. So you can see, to answer this sort of question, we're going to need to know the derivative of an inverse trig function. So let's see how we can figure that out. So to find the derivative of inverse cosine, say, right, the problem is we don't know anything about inverse cosine. The only thing we know about inverse cosine, if we just name this y, so I've sort of changed variable names so that instead of theta I have y, and instead of t I have x, just so that it's compatible with our usual notation for independent variables. The only thing we know about inverse cosine is that it's the inverse function for cosine, at least on part of the domain of cosine. So we could get back to the more familiar function cosine if we just took cosine on both sides of this equation, like this. So that's going to give us cosine of y equals, well, cosine of inverse cosine of x, that's just x. Okay, well, we're trying to find the derivative with respect to x of inverse cosine, so, I mean, we're going to have to take a derivative at some point, and now seems as good a time as any. So let's take derivatives on both sides, right? If this equation, right, this is an equation of functions. We're saying cosine of x, the function cosine of x, is equal to the function x. So that means that their derivatives have to be equal as well. So we can take a derivative on both sides. And we do need to take a derivative with respect to x, because what we're trying to find is a derivative with respect to x. Also, as we calculate this derivative, we have to keep in mind that the original way we wrote it down was y equals inverse cosine of x. That means that y is really a function of x. So as we calculate this derivative, the right-hand side is no problem. The derivative of x with respect to x, that's just 1. But the left-hand side is a little bit tricky, because we're taking the derivative of cosine, but the thing inside of cosine isn't x, right? We're taking a derivative with respect to x. This isn't x, it's y. And y is really a function of x. So you can see we have a cosine function on the outside, but the y function on the inside. So this left-hand side is really a composition of functions of x. So we have to use the chain rule to calculate its derivative. So chain rule says take the derivative of the outside. So derivative of cosine is minus sine. and then we put the old inside into there, that's y, and then we multiply by the derivative of the inside. Well, remember, the inside is y, and the derivative of y with respect to x, that's called dy dx. Okay, but dy dx, that's what we actually wanted, because y is inverse cosine of x, and we're trying to find the inverse derivative of the inverse cosine of x. So this dy dx, that's what we're actually looking for. So let's just solve this equation for dy dx. So we get dy dx equals negative 1 over sine of y. Well, since y is a function of x, dy dx, that should also be a function of x. And the way we have it written right now, it's a function of y instead. But look, y is just inverse cosine of x, so we can use that to turn this y into an x. So dy dx, we can substitute this in. We get minus 1 over sine of y, but y is inverse cosine of x. Okay, well, I mean, it's true. This is the derivative of inverse, right? Y is inverse cosine, so this is the derivative with respect to x of inverse cosine of x. So this is true. This formula is the inverse cosine of x, but the thing is, whenever you have a trig function, an inverse trig function inside of another trig function, you can simplify that, right? This looks more complicated than it actually is. So to simplify this, what we're going to do is draw a right triangle, and we're going to label sides according to sort of how this expression is set up. So this inverse cosine of x, that is, we're putting it into a trig function. So that means it's acting like it's an angle. So in a right triangle, that would be right here. So here's inverse cosine of x, or, right, we call this y. So that's y. And we saw earlier that since y is inverse cosine of x, that means cosine of y is x. So what we can do is label the sides of this right triangle so that the cosine of the angle y is x. Well, cosine, right, in a right triangle, that's adjacent over hypotenuse, so x, we can put an x down here, and I guess we would need a 1 right here, right, because now adjacent side, the x over the hypotenuse, which is 1, is x over 1, and that's x. So what we've done here is we've essentially drawn a triangle picture of this equation. Right? We've arranged for a right triangle to have an angle called y, and so that the cosine of that angle is x. But now that we have this picture, we can find the third side using the Pythagorean theorem. We get square root of 1 minus x squared. And now, using this picture, we can find sine of the angle y. Right? That's just going to be the opposite side over the hypotenuse. So this function that looks really messy is actually just minus 1 over the square root. So 1 over sine y, but sine of y is this square root here, over 1. So square root 1 minus x squared. All right, so there's the derivative of inverse cosine of x. It's minus 1 over the square root of 1 minus x. So that wasn't too bad, and if you look back over this calculation, you probably get the idea that we could actually do this for any inverse trig function, right? The only thing that is going to be different is some details about, right, which derivative shows up here and exactly what this diagram is going to look like. But in principle, we could do this with any of the inverse trig functions. So we did cosine. Let's do sine next. All right, so to find the derivative of inverse sine of x, right, first let's name inverse sine of x. Let's call it y. And then we can take sine on both sides of this equation. We get sine of y equals x. Then we can differentiate both sides with respect to x. Right, this is really following the same flow of calculation as for the inverse cosine example. Now on the left-hand side, again, we have to use the chain rule because y is really a function of x. So we get derivative of sine is cosine. And then we have to multiply by the derivative of the inside, which is y, so that's dy dx. And then on the right-hand side, derivative of x is 1. Derivative of x with respect to x is 1. Now we can solve for the derivative we want. Solve for dy dx. We get dy dx is 1 over cosine y. But we should write this as a function of x because y is really a function of x. We get cosine of inverse sine of x. And now we should simplify this denominator using that same triangle trick as we used for inverse sine. So here's a right triangle. The angle y is down here. And sine of y is x. So to label sides so that the sine of this angle is x, we need an x over here and a 1 right there. And that means the bottom side here is square root of 1 minus x squared. That's just using the Pythagorean theorem. And now we can find cosine of y. Remember, inverse sine of x, that's y. So we can use this diagram to find cosine of y. In this diagram, cosine of y is the bottom side over the hypotenuse, so that's the square root of 1 minus x squared. Okay. And that is dy dx, so that's the derivative of inverse sine of x. Notice that this is actually almost the same as the inverse, the derivative of inverse cosine. It's just cosine had, the derivative of inverse cosine had a minus sign right here, but with inverse sine we get a plus. All right, I think there's one more worth doing, and that's inverse tangent, right? Sine, cosine, and tangent are sort of, they come up more often in applications than secant, cosecant, and cotangent. And so it's the same with the inverse trig function. So let's sort of finish off the big three and do inverse tangent. So we'll name this function, name inverse tangent x, y, take tangent on both sides. We get tangent y equals x, and then take a derivative. Now remember, so we have to do a chain rule again. And the derivative of tangent is secant squared. So secant squared y times the derivative of y, which is dy dx, equals the derivative of x with respect to x, but that's 1. And now we can solve for dy dx. We get 1 over secant squared, but that's cosine squared. So cosine squared y. Remember, cosine squared is really cosine of y squared. Okay, but y, as a function of x, y is inverse tangent of x. So parentheses, parentheses, there we go. I guess I don't need one set of parentheses here. This one doesn't, I don't really need. Okay. So now we need to simplify this stuff here, right? So let's draw a right triangle. Tangent of y is x, so y is an angle as usual, because y is coming out of an inverse trig function, so y is really an angle. And tangent of y is x, so we need to label the sides so that the tangent of this angle is x. So we can do that by getting an x here and a 1 there. And that means that this hypotenuse is, just using the Pythagorean theorem, it's the square root of 1 plus x squared. So now we can use this diagram to write down the cosine of the angle y. So whatever we get for the cosine of the angle y, we're going to square it. But cosine is adjacent over hypotenuse, so 1 over square root 1 plus x squared. But then we need to square that. So what we get in the end is 1 over 1 plus x squared. And this, again, this was the derivative with respect to x of inverse tangent of x. All right, so we've done the big three. Inverse secant, cosecant, and cotangent don't come up as often, so I'll let you calculate the derivatives of those as an exercise. But this is what you'll get. So here are the three that we did: inverse cosine, inverse sine, and inverse tangent. It turns out for inverse secant, cosecant, and cotangent, this is what you get. So for all of the inverse trig functions, we know their derivatives as well.